Okay. Hi, we're World Domination, and the reason why we're called World Domination is because we're proposed to build robots that find each other and shoot each other. Like so it replaces actually what people do, and maybe eventually they'll grow a little smarter and become our overlords. So that's kind of the premise of our project. So we haven't worked. The plan that we're starting with is a mock-up city that we can basically have it find the robot should be able to move through a city, avoid obstacles, find the other robot, shoot the robot, and then know that the other robot's been shot. And that's essentially the premise. So we've had to overcome some obstacles, and the idea is that we've got three main phases of the project. To overcome localization, specifically, we developed a program called Skynet that Scott's going to talk a little bit about.
Okay. Yes, so Skynet is the program we're using to do all the localization. That was one of the biggest problems we had when we were going into this project was, okay, how do the robots know where they are in the world? It's a pretty big problem, particularly in this class, where people who propose to do localization as part of their project usually wind up making their entire project solving localization. So we used some libraries and programs that were out open source in the world. One we're using is called Reactivision. Reactivision takes in, uses the camera and looks for specific markers using computer vision. So for example, it'll see this marker somewhere in its field of view and then replace that with a marker. So on the bottom screen you can see Reactivision running. So you can see it's put a little 1 on top of this marker. Skynet, which is running in the background, is taking that information, parsing it, and creating a game map or a city map. So it's taking the information from Reactivision and creating a map, XY grid, and then sending that information in a specific packet format to our attack robot. So our attack robot knows where it is and where the victim is. So, and as it moves around, it will be sent new packets and update information to figure out where it and the attacker are. And that leads into our next problem, which was getting the information to the robots, which Ned has dealt with pretty much the entire semester.
Right. So what we did is we developed a packet-based protocol. We have a header byte as part of the packet that contains metadata about the size of the packet and what type of packet it is. And then there's a payload that contains the coordinates and the orientation or the angle of the symbols that it's viewing. And to get it to the robot, we use Bluetooth. There's a little board on the robot called the Smurf card, and it presents a serial port to both the Bluetooth, the device that it's paired with, in this case the laptop, and to the Luminary microcontroller in the robot. So they can both just do RS-232 communication, so that's very convenient. We have Skynet print out character-based data, basically. So it takes the 8-bit byte of each packet and prints it to its standard out as a character, and then that gets read in to the standard in of a program called P-Link, which basically talks to the serial port that's connected to the Smurf card. So that's how it gets to the robot. And on the board, then it just basically reads from the serial port in a loop and parses the packet. And so it sounds very simple. We dealt with numerous issues getting that to work reliably throughout the project. And we had some bit patterns that caused problems with the data being received was misinterpreted. And we had to use the right character set in order to get Java to print all 8 bits of each byte reliably. And so we finally worked through all those issues and got it working well. So that's the communications protocol in a nutshell, and we have a little diagram on our poster that you can take a look at that describes what each field of the, or up on the screen here, yeah. So you can see the gray portion is the metadata part, and it also contains bits that describe obstructions and whether or not the robot has a clear shot at the target. And we ended up not using that information in the end. It was kind of a fallback in case we couldn't get infrared working reliably. But we think we have that worked out pretty well, so that's there, but we're not currently using it. And then the colored parts on the bottom are the data payload.
And I'm now going to talk about the breadth first search algorithm and how the robot actually finds its way through the city to the prey.
Well, so now we, so if you look at on the, so the only thing that you have the attacker and the victim. So the only thing that the attacker knows is the victim position. It doesn't know about the obstacle. So now we, so because we utilize the infrared detection, and it comes to so many issues. When we implement the infrared, there are a lot of problems. The stereogram we had before with with using the Skynet information wasn't work really well. So we redesigned the state machine, and so the idea here is try to keep it as simple as possible, because adding a state is increase the complexity. And so look at in the state machine we have here. So basically, we start off with the orienting states. Basically, the robot only moves in 4 directions, either northwest, south, east. And when it's in the orienting state, it's going to try to orient to the desired angle that is going to reach the victim. So it's going to compare the current angle to the desired angle to see whether it needs to turn left or turn right. Once it gets to the correct angle, then it's going to change to the driving state. In the driving state, it's going to move like a square toward the desired angle direction. And once it's moved one square ahead, then it's going to recalculate, do the breadth shot to calculate the next move. And then so when it gets to the row, to the same row in the other column with the victim, that's going to stop and turn it to the shooting stage. In the shooting stage, it have three times that it can shoot the victims. So so it's supposed, when in the shooting stage, it's going to launch the rocket, and if it detects a hit, then it's going to go to the winning stage. If not, then it's going to go back to driving state, and repeating that until it runs out of bullets, and then it's going to be going to the losing state. So that's the idea.
Okay. I'm going to talk briefly about the hardware. So the USB cannon is just being driven by a transistor on that large battery, as you can see, because the current drain would just be too large for the luminary itself. The IR themselves are being fed into the ADC that's on the luminary board, and it's going straight through. The hit detection is probably the only thing that's really unique on our board, and that's there's 2 microphones on in the can. I guess it's a can. And it picks up that sound, it passes through a filter, and then it looks to see what the value is. And if that value is over a certain threshold, it says, I have been detected, and it starts spinning. And that is the essential parts of the hardware.
Okay, and now we're going to talk about some of the major bugs that we encountered, specifically with communication issues, with localization in Skynet, and just recently with the camera a little bit. So Scott's going to talk about localization a little bit.
Okay. One thing that's really difficult with reactive vision and with our camera in general is there's lots of fuzziness with the readings that you get back. If the marker is too close or too far away, reactive vision won't detect it, and therefore Skynet gets no information. So we had to build some workarounds into Skynet to, for example, what happens if the marker is present and then it just vanishes? How do you deal with that, and how do you fix the information? How do you continually send information? And we deal with that by, like, for example, sending the previous or the last sensed location you saw the marker in. Other things like, for example, when we were setting up in here, the lighting is totally different than it was in the lab where we were doing all of our testing. So we spent quite a bit of preparation time this morning just messing with the lighting and getting things to be seen correctly.
Can you talk about the ASCII bug?
Yeah, sure. So I already mentioned we had some problems with the communications protocol. One was that it didn't like the specific bit pattern with decimal value 10. So 00001010 would be read as a 13 instead of a 10 on the board. So we struggled with that for a while. Eventually, we just decided to use the upper 6 bits because all we needed is values 0 through 64 or 0 through 63 were plenty for our purposes. So yeah, it was a cop out, but we had to move on to more interesting problems. So you'll kind of see in our protocol diagram that we have certain fields that must be 0 to work around that silly bug. So yeah, that was kind of a funny one. But actually, we talked to a grad student who worked with this hardware who had a very similar problem, and So we suspect there may be some sort of bug with the driver for the Bluetooth, but we didn't have time to chase that down. And the other thing was, as I mentioned, that the character set was important. When we just had the default ASCII character set, it seemed like Java would not actually print the actual 8-bit value that we were asking it to. And so NAM figured out, I think if we use like ISO 8859-1, which is the Latin character set, it allows for the full range of bits to be used, and that solved that problem. So again, given more time, we could have gotten a sort of more satisfying solution to these problems, but we just found workarounds.
Yeah. So basically, what we currently have working for the most part is we have a robot that's going to actually move through the city and get tracked by Skynet and receive information using, and it'll do obstacle avoidance using an IR detection. That's why everything, if you've noticed, is very conveniently white, because it does seem to read very intensely white and black very, very well. So, so we're actually going to run our demo right now. We've had some lighting issues, so we're going to have to kind of dim the lights a little bit, which might present some issues. But if we do have some hiccups with that, we do have video prepared just in case, so you guys can at least see it working on some level. So, so let's get the demo started. Oh yeah. Well, he made that joke because the 150 in the 150 class we had the same camera and we had a very similar issue.
Yeah, just the middle light switch.
Okay, that's not. Is that the one? That's
No, they got that one.
that one.
There you go.
Yeah. So yeah.
And you got your contrast.
So you can see we've had issues with it tracking when you see the fiducial actually move. Oh, you can't see it right now, but when you see it move, sometimes the contrast will actually lose it because these cameras have an auto contrast.
I'm just testing.
Yeah, so you'll see it rotating, so it does know its orientation, and you see it tracking. It's actually tracking fairly well right now.
It's manual.
Oh, it's manual, okay.
Okay, we're going to do the...
We just wanted to see if the lighting was... We're doing this to see if the lighting is right, because we have had issues where the box will actually skip. So it'll think it's on another node and kind of bounce in between rather than knowing exactly where it is.
Or you just don't know.
Okay.
Okay, guys. Let's do it.
Seems to be working.
Yeah, it's tracking fairly well, so...
Okay.
Okay, so a little
Not
bit
really
of
sure.
the head and you jiggled it.
Black screen.
Another technical issue.
Okay. So it approached it, and the IR sensor actually hit it, and and it's actually avoiding the obstacle. But it does know where it is, and it knows where the target is.
Yeah.
So it's doing a breadth first search every single time, and each of those maps is treated as a state, and it's finding it. So it's actually just determining the best path to go. It's supposed to.
There's some definition of the best.
Some definition of the best path. Very loose definition of it. Okay. It's going to back up a little bit. It's got to warm up.
It also has to get in the correct orientation position for the optimal shot.
Yeah. You can't just go around killing people. You know what I mean? You gotta make. Oh no.
It'll try again.
It'll try again.
So our very sensitive hit detection is not.
I know, right?
Now you get to hear the losing.
That's Bluetooth.
There we go.
Alright. Of course, it was working much better in the lab.
Well, in a perfect world, right? But anyway, that's our project, and that's what we have working. So I hope you guys enjoyed it.